Welcome to project number 6, Pulse Counter. Let's have a quick project overview. In part 1 of this project, we are going to design in Verilog the following modules: a pulse counter, a debounce module, and a 7-segment decoder. Next, we are going to do 2 Verilog test benches for the debouncer and the pulse counter. In the end, we are going to do Modelsim projects and simulations. In part 2 of this tutorial, we are going to create a Quartus project, synthesize the top module, connect the design to the FPGA pins, and in the end program the DE1 SoC board and do a demonstration. The synthesis result of your Verilog code should look like this in the end. The project is going to work in the following manner. Whenever you press I push button or the I switch inputs, a counter will increment and the 7-segment display will show the total number of pulses. You will also get to see what happens if you directly use the signal coming from a mechanical switch and how can you fix all the issues coming from this. If you are a complete beginner, I recommend you doing some of these easier projects before starting this one. They will help you easily master the Modelsim simulation and the Quartus synthesis workflows. Here is the block level diagram for the pulse counter. I button enters a Schmitt trigger, which is on the FPGA board, and after this it enters a 4-bit counter that increments on its positive edge. The result is displayed on the 7-segment display number 0. I switch enters the FPGA and is distributed on 2 paths. The first one enters the Debouncer module and the filtered signal is passed next to a counter. What happens from here is identical with what happens for I button. The second path of I switch will enter directly in counter number 2 that will increment on the positive edge of the signal. What do you think about the values for counter 1 and counter 2? Are they going to be equal or different? Let's analyze the top level port description for the pulse counter. The module has 2 parameters. The clock freq, which has a value of 50 MHz for the DE1 SoC, and the stable time milliseconds that shows how many milliseconds the value of the push button should be stable. The first 2 inputs are the clock and the reset N. Reset N is a asynchronous active low reset signal. I switch and I button are 1-bit inputs, one coming from the switch, which is noisy, and the other one coming from the button, which is already debounced. OHEX 012 are 7-bit outputs going to the 7-segment digits. On this we are going to see the hexadecimal value of the 4-bit counters. Let's see what happens when you press a mechanical switch. The physical bouncing of the mechanical contact produces pulses in the microsecond or the nanosecond range. This could trigger multiple times a device's functionality. This phenomenon requires debouncing. It can be done using an analog circuit, a digital circuit, and in software. In the first image over here, you can see a simple schematic for a button that will generate a logic 1 when it's pressed. Before reaching a stable value of logical 1, it will generate these tiny pulses over here. The same phenomenon happens when the button is released. So instead of having only 1 pulse when you press a button, you will get at least a few tens of extra parasitic pulses. This can be easily fixed by using a Schmitt trigger. Schmitt trigger devices are typically used in signal conditioning applications to remove noise from signals used in digital circuits, especially mechanical contact bounces in switches. My development board, the DE1 SoC, uses a Schmitt trigger for the push buttons. The user manual says like this: since the push buttons are debounced, they can be used as clock or reset inputs in a circuit. Here is how the push buttons are connected on the development board, and here is how the Schmitt trigger will filter all unwanted pulses coming from the push button. As a small mention, by default, the value coming from the push buttons will be a logical 1, and when you press it, it will become a 0. Let's analyze this digital circuit schematic used for debouncing. There are many solutions for a debouncing circuit, but I choose this as it provides flexibility and can be used in many other projects. It uses 3 flip-flops, 1 XOR gate, and a parameterizable n-bit counter. The first two flip-flops are used to fix metastability issues, and the XOR gate will have a value of 1 when the values of the two flip-flop differs. This happens when you have a transition on the value coming from the button. This will clear the counter and it will start again counting from 0 until the end of the stable period. The output of the circuit is updated with the value coming from the button after the stable time finishes. The size of the counter varies with the clock frequency and the desired stable time. Usually most switches have a stable time after 10 milliseconds. A 50 MHz clock requires a 90-bit counter to have 500,000 clock cycles to be stable. If you want to know more about this circuit, you can look on the DigiKey forum. And now it's action time! Please create the following Verilog files: Debouncer, hex 7-segment decoder, Pulse Counter, TB Debouncer, and TB Pulse Counter. Note that the full project can be downloaded from ovisign.com/courses. Let's implement first the Debouncer circuit. This circuit has two parameters. The first one is used to define the clock frequency that we are going to use. The second parameter shows us how many milliseconds the input signal should be stable before passing its value to the Debouncer output. Next we have the port section. We have the clock, the reset N, the E-debounce, and the O-debounce signal. Here we define a local parameter that will help us reset our counter when this value is reached. This formula for these two parameters shows us that every 500K our counter will reset. If you multiply 500K by 2, you will get 10 milliseconds. Now we declare the internal logic of the module. We use a 2-bit vector for the flip-flops. The FF_I are these two flip-flops over here. Next we declare a 24-bit counter. This should be more than enough for most frequencies. These two wires over here are going to help us create the clear counter logic. The clear counter wire over here is the output of this XOR gate. The counter max is when the counter reaches the maximum value defined by this parameter. The first two flip-flops are used to eliminate any metastability issues coming from the input signal. I decided to code them similar with a shift register. The clear counter signal over here is created using the XOR reduction operator. Now let's create the counter logic. Remember that this can be implemented in a number of ways, but I choose this one. At reset N, the counter is cleared. Next, if we reach the clear counter or the counter max condition, we clear the counter also. Otherwise, we increment the counter by 1. If we look at the Verilog code, we can see that the clear conditions have a bigger priority than the increment condition. So whenever one of these signals occur, you are going to be sure that your counter is going to get cleared. Now we create the counter max value, which is a simple comparator that compares the value of the counter with the parameter counter max. In the end, we have the output logic for the last flip-flop. This flip-flop is cleared by asynchronous reset N, or if counter max is set, then the output flip-flop will get the value from flip-flop number 2. In the end, we connect the output of the module with the output of flip-flop number 3. This is it. Let's implement the test bench now. Please make a new file called tbdebouncer.v with the following content. Because this is a test bench, we first declare the timescale. After this, we have the test bench variables. We declare the inputs in our module using the reg type, and for the outputs we use the wire type. This reg variable over here is going to be used to create parasitic pulses on the input signal. Next we have the half value of the clock period. Here we instantiate the DUT. We connect the module's ports with the test bench variables. Here we create the clock signal, and here we have the test scenario. Initially we have our device in reset and the input equal to 0. After 5 clocks we release the reset. To make the scenario more realistic, we wait for 1500 clocks. Here we generate some noise on the input signal, meaning that the button is pressed. We first assign to our 7-bit delay an unsigned random value. Next, we wait that random amount of time and toggle the input in our debouncer. This will create the input parasitic pulses. After this, we stabilize the output to 1. This line over here makes the test bench wait for O debounce to settle to the value 1. This should take around 10 milliseconds to synchronize this part of the test bench with the DUT. Next, we wait for some more time, and then we create the same noise on the output signal and stabilize the input to 0. After this, we wait again for the O debounce to become 0. We repeat the whole scenario 2 times. This should be equivalent for pressing a button 2 times. In the end, we wait some time and stop the test bench. Let's see what happens on the waveform now. Please create a new Modelsim project and start the simulation. If you don't know how to do this, please watch one of our previous tutorials like FPGA project number 3, binary adder to 7-segment display. Let's see what happens on the wave now. We zoom on the beginning of the test scenario, and we can see how the input debounce signal has some parasitic toggles. Let's watch what happens with the counter. Here iDebounce is set to 1. Next, we see how flip-flop number 0 and flip-flop number 1 are set. Because the value of these two flip-flops is different in this clock cycle, this will set the clear counter signal, so in the next clock the counter will become 0. If we zoom out now, the counter starts counting. Here iDebounce toggles again. This will make the values of the input flip-flops also different, so clear counter is set again, so the counter starts again counting from 0. And so on. This happens whenever a pulse on iDebounce occurs. In the end, after the last pulse on iDebounce, the counter will start counting and it will stop until it reaches the value of 10 milliseconds, which is a very long simulation time. So you see that it reaches the value of 500,000 over here, and next the counter becomes 0 again. When the counter reaches the maximum value, you can see how O debounce takes the value of E debounce. This is it. If we measure this on the wave, you will see that we have a 10 millisecond difference between the moment when E debounce settled to 1 and when O debounce gets the value 1. Now we simulate the scenario when the button is released. The same pulses occur when the signal transits from 1 to 0. Now our counter will repeat the same story. You will see how it gets the value 0 over here, and here it is cleared several times. In the end, O debounce will eventually get the value 0. So we still have the same 10 millisecond difference between the moment E debounce was cleared to 0 and O debounce was cleared to 0 also. This is showing us that our debouncing circuit is working correctly. You can play with the test scenario to see what happens when you add multiple pulses or when you change the number of milliseconds the counter should be stable. Let's create now the 7-segment decoder. I won't insist on this code as it is proven to work on the FPGA board and in multiple projects. Let's implement the pulse counter top-level module. These two parameters are the same as for the Debouncer module. Next we have the input clock and reset N, the I switch input, the I button, and next the outputs for the 3 7-segment displays. Here are our 3 counters. The first one connected with the button that has a Schmidt trigger, the second one connected with the switch which is debounced, and the third one which is not debounced. This wire over here is used to be connected with the output of the debouncer. Here we have the logic for the first counter. Instead of pause edge clock, I use pause edge I button to increment the counter with a 1. In general, you should use only posage clock. An I button should be inserted in the logic inside the always at procedure. But I use this to reduce the number of logic elements inside the circuit and also to prove what happens when a noisy input is inserted inside a digital circuit. Whenever you press the button Debounce with the Schmitt trigger, this will increment the counter by 1. It's that simple. Next, we instantiate a 7-segment decoder and connect the counter at the input and O-hex 0 at the output. Let's implement now the counter for the debounce switch. As I said, the switch is a very noisy input, and the debouncer module will help us clean that noise. We connect the module ports with the local signals. The I switch is connected in the input of the debouncer, and the switch debounced is connected to the output of the debouncer. Next, using the same logic as above, on posage of switch debounced, we increment the counter by 1. Here we have the corresponding 7-segment display instantiated. In the end, we have the counter for the switch which is not debounced. This counter will overflow several times before having a stable value. Let's see how our design behaves in simulation now. Please create a new module called tbpulsecounter.v with the following content. These are the testbench variables connected with our DUT, and these are some parameters used in our test. Here we instantiate the pulse counter. Next we create the clock signal, and in the end we have the test scenario. The test scenario is very similar with what we use for the debouncer. In the first part over here, we are testing the push button which is supposed to be already debounced. We first wait for 20 milliseconds and then we toggle the value of the button. We repeat this 5 times. In the end, we settle the button value to 0. Now our second test scenario is identical with what we used for the debouncer. We first create some noise on I switch. Then we settle the value of I switch to 1, and now we wait until we see a transition on hex 1. Next we create some more noise and settle the value of I switch to 0. We repeat the complete scenario 2 times. Let's see how the switch counters behave in simulation now. Before starting the simulation, please make sure that you have the following Verilog files in your project. You should have 5 Verilog files. Add all the Verilog files in your project and start the simulation. We will now focus only on the internal signals of the pulse counter. We add them in the wave and start the simulation. You can see how the simulation consumes a lot of time, but this is not bothering us since we want to see the real behavior of this module. We can see in the console how the 2 test scenarios executed. First, as we discussed, we create pulses on the I button input. This doesn't have any parasitic transitions because it is already debounced. You can see that whenever a posage occurs, counter 0 increments with 1. So it settles to a last value of 2. Next, let's check out what happens with counter 1 and counter 2. Here we have the first transition on I switch. As you can see, it has some parasitic transitions. Counter 1 is not incremented when these parasitic toggles occur, while counter 2 is incremented on every posage of I switch. This is showing us that the design is counting also the parasitic transitions. This is very bad. Imagine this happening while you press a button on an elevator. You can see how counter 1 is incremented to 1 only after 10 milliseconds of stable value have passed. Next we have a 1 to 0 transition on I switch. Let's see now what happens. We also have some parasitic pulses here, so counter number 2 is incorrectly incremented again. While counter number 1 is not incremented here because it counts only posages. Next, on the following posage, also with noise, counter 2 is incorrectly incremented, while counter number 1 is correctly incremented to 2 10 milliseconds later. This simulation shows us that our debouncing circuit works correctly. Let's see in part 2 how we can implement our project on a real FPGA board. If you like this tutorial and you're interested in an easy path for learning Verilog for FPGA or ASIC design and verification, I gladly recommend you my course Verilog HDL Fundamentals for Digital Design and Verification. You can find the link in the video description. For more tutorials and support, you can join our Facebook community. Your strong Verilog foundation is only one click away.